In this example, we're looking at two connected particles. We're told two particles, A and B, weighing 1 kilogram and 2 kilograms respectively, are connected by a light string and hung over a smooth pulley fixed to a rafter. The system is supported so that the string is taut, then released. Find how far the 2 kilogram particle will fall in the first second of motion. So we're going to go through and look at this question and break down the parts. The first thing is we need to draw a diagram. Now I have drawn a diagram here showing the full system. When we're solving these problems, what we do is we draw the diagram into two parts, which we will do shortly. The first part looks at particle A, the second part looks at particle B. So what do we have? We have a pulley that is fixed to a rafter. A rafter is a wooden beam. And what we have is a pulley fixed to the wooden beam. So a pulley is fixed to the wooden beam. What I've drawn there is a three-dimensional version of our pulley. The string fits around the pulley and comes down the other side. So, going back to my other drawing, where the circle is, here, that is the pulley. The string goes from particle A around the pulley to particle B. Now we've been given a lot of information. The first piece of information we'll look at are the weights. We are told particle A is 1 kilogram, so we know it has a weight of 1 g. That 1 g will be a force operating towards the ground. I've just highlighted it on the diagram. We also have a weight of 2 kilograms. That is also operating towards the ground. 2 kilograms is going to be 2g as my weight. I've now highlighted that. Now there are some other pieces of information that we are given. We are told it is a smooth pulley. Now previously, when we have looked at something being smooth, we've talked about it as not having friction. Here, what we're saying is when we're looking at a smooth pulley, that the tension in the string is the same throughout. The tension I have represented by T. So what we have is the string, which I'm going to mark in blue. The string goes from the center of particle A to the center of particle B. In that string, there is tension. For particle A, the weight is pulling down, so there is a force in the string which is going up. So I've marked on the diagram T, the tension force going up through the string. Similarly, for particle B. Particle B has a force of 2g going downwards, which means there's tension in the string going upwards. It is also T because, as we said, the pulley is smooth, so by that it tells us the tension of the string is the same throughout the string. If the pulley was rough, then we would have different values for the tensions for both particles. We're also told that we have a taut string. Taut can also be said to be inelastic. I've highlighted taut in both pieces of writing. So the system is supported so that the string is taut and then released. So it's held in position, then it's let go. Now, 2 kilograms is a heavier weight than 1 kilogram, which means the 1 kilogram weight will go up, the 2 kilogram weight will go down, so the motion is going to be the 1 kilogram going up and the other side with the 2 kilogram going down. So we can see which direction the motion will be. The acceleration will have the same magnitude for both objects. So both sides have the same magnitude of acceleration. Because acceleration goes in a direction, and it's going to be in the direction of motion, we're saying magnitude, because the reality is going up, we could say, is the positive direction. That would be acceleration would be positive, but the second half of the diagram, then we have the particle going down. So we would say the acceleration there is negative because it is going in the direction of the motion. Now we're going to look at the 2 diagrams that we would draw to solve this problem. If you look at our 2 diagrams, particle A, which has the weight of 1 kilogram, showing the 1g going down, and the tension in the string up, because this was moving in an upwards direction, acceleration we've got going up in the positive j direction. Like we've done in previous exercise then, we can say the vector for A is equal to the magnitude of A times j. Similarly, for particle B, it has a weight of 2 kilograms, so there is 2g going down, tension in the string going up. They are the 2 forces acting on particle B. Particle B, though, is going to be dropping down, so you can see for the acceleration we've written negative ag, negative because the direction is going down. So we now approach the 2 particles separately. So for particle A, the motion equation is R equals ma. Now, R is going to have T going up, so a force of T going up, and a force of 1g going down. So that is T minus 1g, and that is in the j direction. On the other side, we have mass times acceleration. Now the mass was 1 kilogram, and the acceleration we've called a, and that is also going in the j direction. So that gives us t minus, instead of writing 1g, we write g, is equal to a. We do not need to write down the j's. There is an equation we have. Remember, g is a constant, so we have two variables in there, t and a, which we can solve simultaneously shortly. Now, if we look at particle B, same thing, we can look at its equation of motion, R equals ma. This time we have t going upwards, and we have 2g going downwards. So the forces acting on the particle B will be t minus 2g. That is also in the j direction. Now, when it comes to the acceleration, we have ma. Now, m is 2 kilograms. For our acceleration, remember we were going in the negative j direction. This is shown here. What that means is, when we write our next line, t minus 2g is fine. Do not forget to go minus times 2 is negative 2a. I have then multiplied through by a negative so that I get positive 2a. So I have 2g minus t equals 2a. Again, g is a constant, t and a are variables, so we now have simultaneous equations. I have added equation 1 and equation 2, and you could see I get g equals 3a. So if I divide both sides by 3, I now have acceleration equals g divided by 3 meters per second squared. But the question wanted to know how far the movement of B was in the first second. So we know the particle started at rest, so its initial velocity was 0 meters per second. So u is 0. We're looking over 1 second, so we know time is equal to 1, and we've also worked out acceleration. Now g is a constant, so a constant divided by another constant, a number, is a constant. So what we have is constant acceleration. So using one of our constant acceleration formulas, s, distance travelled, equals ut plus a half at squared, we can substitute into that. U was 0, t was 1, and a acceleration was g over 3. Working that out, we get g over 6 meters